All right. So we have eight folks online. So the video's on, audio's on. Can I get a thumbs up from somebody that you can hear the audio?
Yeah, all good.
Okay,
We're good here, yeah.
thanks. So I'm going to share my screen and go to PowerPoint. Okay. Then this is lecture 2, so I think we're on our way. Okay, great. Get rid of this. Okay. Perfect. Good. Okay, great. So we're going to start today with image quality, and we'll do a little bit of X-ray physics as well towards the end. So the last 20 minutes will be X-ray physics. I think there's about 8 people online at this point. So from my perspective, you're welcome to attend online if that's easier for you than commuting here, whatever. That's perfectly easy. Hey, hi. So it's easy to do that. Also, one of the advantages of watching the video of the lecture is that you can watch it in 1.5x or 1.75x, which is way more efficient. In fact, when I'm watching videos, I always do that, even reviewing what I do before I put it there. And then when you flip back to 1.0, it truly does seem like I've had a bit too much to drink, right? It's a very interesting transition. You get used to this amphetamine-fueled lecture style, right? And it's great. I mean, things really rip through. So that's fine with me if you want to attend online, if you want to watch the lecture afterwards in 1.5x or whatever. We have pre-recorded lectures from 20 and 22. So last year's lecture is up there on YouTube, and here's the link. It's open to the world, so anybody can get into that. And how did it go getting Canvas? Does anybody still not have access to Canvas? Okay, great. All right, that problem got fixed. You have to thank Tom for that because he got that fixed. Okay, so we're going to dive into defining image quality and a very general concept, right? So here's 3 different images from different modalities. This is X-ray CT, this is MRI, and this is positron emission tomography. And they obviously have different appearances, right? The contrast between different types of tissue in the MRI is quite stark. The gray matter is this darker tissue here. The white matter connecting tissue is the lighter tissue, and the CSF is dark. In the brain, it looks like all soft tissue looks the same in this CT image, right? So there really isn't a lot of contrast between different types of brain tissue in this image. However, modern CT scanners can produce images that have much better contrast than this, but you can see there's slight contrast between the eyeballs and the background, but that's about it. So a compressed contrast. And here, the major difference between, say, positron emission tomography in this patient and this person in MR and positron emission is that the spatial resolution here is a lot lower, i.e. it's blurrier, right? And one of my favorite comments from a clinician when we were doing a very novel sort of cardiac imaging thing where we painted lines on the heart and we watched these lines deform over time. This is back 30 years ago. And the cardiologists that were interested in this are all standing around the screen. This is the first time they'd ever seen it. Actually, in person, the first time I'd ever seen it. And so we're looking at it, and then one of them goes, can you focus it a bit? Right? Which is, a way of saying, hey, man, increase the spatial resolution, right? Because it's just not sharp enough. It's just too blurry. So if I had a focus button, we all have a focus button in general on these imaging techniques. So the concepts that are in the book, in the chapters and prints and links that are discussed, in technical detail there, and we'll look at the definition of all these things. And if you have all of these in your pocket, and you're trying to evaluate whether or not your imaging system is performing well, and you evaluate this stuff, it's pretty good. So contrast will define, which is just, is there a signal difference between two different types of tissue? Spatial resolution, one way of defining that is, can I resolve two small points that, if I have two small points in my scanner, how close together can they get when I can't resolve them anymore? That's one way of defining spatial resolution. Is it one thing or is it two things, right? Temporal resolution, do I need 10 milliseconds to make an image, or do I need 5 seconds, right? And so what happens across that 5 seconds? Do things move? Do I have to average over that 5 seconds, or are they sample shots that are added up together over the 5 seconds? So temporal resolution is an interesting topic in MR and CT, actually. Noise, where does it come from? You basically look at any picture, and there's random signal in that picture. Sometimes you don't appreciate it because it's so low, but it's always there, actually, the random signal. And in medical imaging, usually what gives you more noise is if you have, say, fewer photons to image with. So you have a lower dose scan, you'll have a higher noise field. In MR, if you scan for a short period of time and you acquire your signal really quickly, you won't get a lot of signal, but you will still get, commensurate noise. And so the signal to noise will be low because you haven't averaged that together. And then when you take the signal and the noise, you take the ratio, it gives you kind of an idea of where you're working, in terms of, do I have a positive signal above the noise level? Similarly, with contrast to noise, can I see the difference between two tissues given my noise background? And we'll see some particular examples of that. So in the book, when they're talking about signal and a way to, mathematically look at a particular signal, they use a sine wave, and it's pretty simple, right? So the formula is down here, and it has a DC level. So there's a background level that this image has that's constant. And then on top of that, there is a sinusoidal function that is oscillating, right? And these two constants here. So if I set A to my background level, which is called the DC, and then B, I sort of change the amplitude a little bit each time and take a look at the picture. Here is when B is 0. There's no oscillation. There's no contrast or signal other than the DC background, right? It's just a constant field. Very simple image. Here, we start to see spatial variation in the signal, right? By setting this constant, right? Or the ratio of these two constants. We had to complicate it, but, increasing the B value, and then increase it more and increase it more until finally I'm at a very bright, dark sine wave, right? Which you can appreciate quite easily. And so the question is, at what level does that amplitude have to be to detect that sine wave above the noise level? In this example, there is no noise. And so this signal is, every pixel has the same value. So there's no noise. It's a mathematical picture. But characterizing your imaging system so that you know how it performs on signals like this is actually quite important, because you can characterize any function as a summation of different sinusoids using Fourier theory, right? So any function you have, you can reconstruct that function as a linear summation of different sinusoids with different frequencies. So knowing what your system does to this signal is a good thing, right? You can imagine that the ability to resolve that sinusoid, not just the noise, but if I put more and more oscillations per unit space, I'm eventually not going to be able to resolve them. So if you think I have a striped pattern on the wall and I take a picture with my camera, in the picture, I see a striped pattern, and then I push the stripes closer together and I take another picture, and I push them closer together, I take another picture. Eventually what happens with this camera, because it has a finite resolution capability, is those stripes get so close together, it just comes out as an average value, right? You don't see the stripes anymore. So that camera cannot detect that spatial frequency, right? You've gone beyond the ability of that camera to detect it. So You can do that experiment at home. I had a staff scientist who was an avid photographer, and he bought all these super expensive cameras, and he was always making these patterns they would put up and test all of the lens and detector systems on these cameras. This was well before you posted junk on YouTube. So, but he would have had some great stuff had he recorded any of it. So let's look at how you quantify what happens to a signal like a sinusoid in an imaging system. So we have a input, and think of these, right? It's just one of these pictures. It has a sinusoid in one dimension, okay? And it has a specific amplitude of that sinusoid. When I take a picture of it with my imaging system, usually what happens is, depending on the frequency of this sinusoid, the amplitude of the output of the picture will decrease, right? And so particularly as I get to higher and higher frequencies, I see a higher and higher decrease in that amplitude, until eventually this thing is oscillating so quickly that my imaging system cannot basically detect it as an oscillation, and you come out with just zero, right? And what you can do to characterize this ability of the imaging system to resolve different frequencies is you can just do that. You can make a test pattern where you have a striped pattern with certain spatial gaps in it. Now, this is a square wave. It's not a sine wave, but it's closely related, right, to a sine wave. And so I have a square wave of different gap spacing here. And then I decrease the gap spacing, decrease it again, decrease it again. So that's the input function. And what comes out of my imaging device looks something like this. So this is, I can determine the peak amplitude between the dark and the bright stuff, and it's really hasn't attenuated that much, like maybe a couple of % here. But then as the frequency goes up, that attenuation of my imaging system also goes up. And so now the amplitude between the dark and the bright has been reduced until finally I get down here where they're very close together. Is that everybody? Well, I'm glad we're all on the same page. Did anyone know that was going to happen? Oh, you did? Oh, okay. All right. Did they tell you what time it was going to happen?
Yeah.
Oh, okay. Cool. Because you're driving in your car or whatever, that's dangerous, man. Everybody on the 5 right now, all their phones are going off and everything. Jeez. You can have a big wreck, you know? Okay. Well, that was exciting. It's too bad it didn't happen at a more like exciting moment in the lecture, like just some crazy thing. But anyway, okay, so this function, so if you plot how these amplitudes go as a function of frequency. So this is spatial frequency here, and spatial frequency, you have at the end of this course, you will really understand what this term means, okay, spatial frequency. And it's the number of cycles per centimeter of this spatial pattern, okay? Sorry, you're late. We're all in the bunker by now. You're left out. Where is everybody? Oh my goodness. Okay. So, if I just draw a pattern on the floor and it's a sine wave, it has a certain number of cycles per centimeter, right? That's its spatial frequency. And what we're doing here is we're measuring the decrease in the power of the signal that comes out. In this case, it's the amplitude of the signal that comes out as a function of increasing spatial frequency, okay? Sorry, I wonder what that delay is about. Oh, maybe, did we have to shut it off somehow?
Yeah.
Oh, it just came back on? Okay, weird. Who's behind this? Who do you think did it? Like, is it a federal government thing?
Yeah.
It is? Okay. Okay. So if we did this for every, many spatial frequencies along here, and we plotted this function, the blue line that fits all those values for the decreases, that's called the modulation transfer function. Okay. It's a very important concept in imaging, because if I ask you, well, just, what is the spatial resolution capabilities of this system? You can produce a graph and say, this is the modulation transfer function, and that's it. We're done. I know exactly how that, system transmits higher frequencies. So what happens with all imaging systems is eventually you reach a spatial frequency at which you can't detect that signal anymore. And so it rolls off to zero. And so that could be, depending on what imaging system you have, that could be centimeters, it could be microns, could be picometers, right? Depends on what your imaging system is. And this happens with like telescopes too, like the Webb. You say, well, what is its angular resolution? If I had a sine wave in the background, or I had stars at a certain frequency, can I resolve them, right? Okay, so we're going to build these modulation transfer functions for our imaging systems. We're always going to know what that is. The manufacturers will state what their modulation transfer function is in different ways. Some of them will give you the half height. Most of the time, this function is well fit by a Gaussian or a normal distribution. If you don't know what a Gaussian is, go to ChatGPT and say, give me a Gaussian. What does that look like? It'll give you the formula perfectly. And so you could get the half height. A lot of manufacturers will choose a cutoff like 10%. And they'll say, okay, our modulation transfer function has a 10% cutoff at 4.2 cycles per millimeter. And that's what they give you as the statistic, right? So but you have to be careful, because sometimes this in here, there'll be details that misses, right? So here's a very practical example of what it looks like when you change the modulation transfer function on your imaging device. And so this is a CT scan of a two-dimensional object. It has holes here, which give a CT Hounsfield unit of 0, and then a background, right, which is, I don't know, 600 or something like that. And it has a pattern of holes which get closer and closer together, right? This is an image obtained with, a minimum amount of X-ray radiation. So we'll say it's 50 milliamps or going through the tube or something like that. And then when you turn that up, it turns into this. So if we increase the number of X-rays, we get this picture. Decrease, we get this picture, okay? Two things are happening. In the background, there's higher noise here than there is here, okay? So you have higher certainty of your values, even when you don't care about spatial resolution, like in the background, right? But also, and this is something about CT scanning, the manufacturer, when they get down to a low number of photons, they will start averaging things together in the raw data. And when that happens, they start losing spatial resolution, right? In order to keep the signal to noise of the background reasonable, they'll start averaging stuff together. And so it affects the modulation transfer function. And so if let's look at a specific set of holes like this here. So if I draw a line, we'll see that we can see an up and down pattern. And then in this, oops, we'll do that. And then here, that pattern basically goes away, right? It's all just smushed together, right? So you can't resolve it anymore. So we can quantitatively measure the modulation transfer function on our imaging device by taking a picture of something like this, in this case, CT. We could do it with MR2. And then take a line and you'll do this for homework in using a piece of software. The one that we suggest is called ImageJ. It's a public domain analysis package, which will be posted up, Yeah. Yeah, sure. If you increase the number of photons, so the question is, what is the relationship of signal to Okay, this is a really interesting question. So, and I'm going to repeat the question so that we make sure I get it right and people hear it. So as we increase the number of photons that we use to make an X-ray image, whether it's an X-ray image or CT, as we increase the number of photons, the signal to noise will increase as the number of photons, or in some functional way. And the question is, does that effect eventually saturate? So is that increase going to go up, say, linearly or whatever, and then saturate such that even though I'm putting more photons in my system, my signal to noise does not go up? My simple answer to that is no, it does not saturate. You just get more and more confidence, lower standard deviation around the value that you have taken. Yeah.
But on MRI, though, it will eventually saturate, right? Because your receiver won't be able to grab.
Well, the interesting thing about, in MRI, you have a certain amount of signal to noise, and you have to think of it in MRI as kind of per unit time, because in MRI, you acquire data over a certain time period. And if I increase my data acquisition by 2x in time, I can average that data together. That doesn't saturate. I can just average and average and average and average. And we've taken images over weekends where we take a heart in a jar, you put it in the scanner, and you image it over 40 hours, right? And your signal to noise just keeps going up and up and up and up.
But if you were to just put another signal in there, like if you were to transmit something with high power in the bandwidth of the receiver, eventually it would saturate.
No, I don't think so. I think if, say, and this is the miracle that could occur one day for MRI. MRI is based on a very small percentage of spins being oriented in the down or lower energy state versus the up state. And that's called the polarization of the material. And it's a really small percentage. It's like 1%, less than 1%, is 0.06 or something. However, some materials you can superpolarize, right? So if you could polarize water in your body to like 100%, the signal you would get out of an MR scanner would be ginormous, right? And my feeling is, as that signal goes up, your signal to noise just keeps going up, because the noise is essentially random motions of molecules in the body. That stays constant, I think, right? And random electronic noise in your parts and your coil and your resistors and stuff like that, that stays constant. So if you change the polarization, your signal noise just keeps going up, I think. And so if you want to win the Nobel Prize, figure out how to image hyperpolarized water in people, right? Or hyperpolarize a human in a magnet somehow, right? Yeah.
How does the signal to noise ratio change with the intensity of light? Because I don't know if there's a formula or a law.
Yes. Yeah, there is an analytical formula for all of these techniques, for every imaging technique. Physicists have sat down and said, okay, what is the formula for signal to noise under certain circumstances? Because you usually have to give yourself some kind of boundary circumstances for that. But yeah, that is there. And it's probably in the book, actually, for this. Well, there's multiple parts to signal to noise in something like CT. There's photon counting error. There's electronic noise. There's, you know, basically, I guess that's essentially the two big ones. Say again? Yeah. Yeah. Well, that's what we're going to quantify now in this little discussion about signals to noise and contrast to noise is based on what you can measure in an existing picture, right? And so there are, you know, there are other ways you can measure sort of the noise output of a system or whatever, but what we'll look at right now is a very practical way to determine, say, what the contrast to noise is for my imaging system, right? Through these measurements. Yeah.
The detection method or the receiver for like any of these methods have like a cap on the signal that it can bring in. That's kind of more what I mean. It's not that the signal goes up, but
Yeah. I get that. So, well, you could imagine in MRI, for example, what is the maximum voltage that your receiver coil could measure, right? So you have a transmit coil which can produce ridiculously high voltages and currents, and a receiver coil that's usually down in like millivolts, right? And so if all of a sudden you had signal that was large enough to be volts, it probably would just blow the thing up, right? Which we've done before. If you don't decouple your receiver coil from your transmitter coil, you can transmit directly into your receiver chain, and that will just fry it with too much signal.
Sort of thing on CT? Like if there is a cap or no cap?
There would be a cap, I think, in that if there were too many photons per unit time, you might saturate the detector, right? It would just get to a certain flashing brightness and then it wouldn't get any brighter, right? Yeah. But we usually design the system to work in the dynamic range that you expect. And then if that detector was like at CERN and it was going to do a high energy experiment where they had lots of stuff happening per unit time, then you would need something that had higher dynamic range, right? Yeah.
How close is like the current maximum like amount of energy in CT relative to like the statistically like safe amount for humans?
Oh, I see. Okay, yeah. Well, so the question is like, how close are we to the maximum, you know, achievable sensitivity for high photons versus what you are willing to give a patient, right, in terms of dose. And what we're willing to give a patient is it's decades, orders of magnitude lower than the ceiling of the detector, right? However, when you're making a picture, there are parts of the detector that are outside the patient sometimes, so it's just a straight shot from the source into the detector. So you have to be able not to fry your detector or also measure that kind of fluence. But usually, because there's a human in the scanner, you've cranked everything down to a low level because you don't want to give them a lot of radiation dose. So it's usually working at a pretty low level. In fact, you have contrast agent in, say, the left ventricle, and your X-rays are going through there. Oftentimes on the detector, so it takes 1,000 views. In each view, if you count up, like how many photons hit my detector for the signal on that view, it's like 5 or 10, right? So we're getting way down into the counting noise of photons, but it goes up in decades, right? It can then be 10,000 in the one over here because it's in air, right? All right, this is great. I've never had this many questions before for this course. This is great. Okay, so and by the way, a combination of answering these questions plus the lecture from last year. If we don't get to where we're going, you can watch it online and we'll get there. Okay. So here we have a CT scan. We're going to measure the oscillation of the signal created by these holes that are drilled into this material at a certain spacing, right? And when I plot the signal value in the pixels across that red line, I see this graph. Okay, so the peaks are at about just over 150 and the troughs are somewhere on 100 or 90, something like that, right? So I see this modulation, right, coming out of my imaging system. And then when I look at that modulation for the image that was obtained with many fewer photons, like perhaps a factor of 20, right, then what happens is smoothing is done in order to decrease the noise in the image, which essentially smooths out these details at this frequency. And so now we see this plot, right? And you've essentially wiped out that frequency. So the MTF has now moved in towards, zero frequency. Another way of looking at resolution, as opposed to looking at a sine wave function like that and how it changes for different acquisitions, is to ask the question, if I have two very tiny points and I image them with my system, how close can I bring them together before I cannot tell that they are two things anymore, right? That's Raleigh's definition of resolution. Is just like, how do I get these two, how close can they get together, right? And so here's the two objects. Here's one at x1 and one at x2. And we're going to bring those two objects together to see when we can't resolve them. This function here is called the point spread function. And the way we derive that is we image an object that is really tiny. Okay, so if the way we do it in CT usually with our scanner is we'll break a ballpoint pen and we'll take the little 0.5 millimeter ballpoint out of the pen, which is a little tungsten sphere, right? And you put that in the scanner and take an image of that. That thing is way smaller than any pixel that is, shown on the screen as an image, right? And so when you make a picture of something so small, it doesn't come out as one pixel, as a spike, 1 pixel. You choose how your pixels are distributed such that you can see this function, which is the point spread function of the scanner. And so the tiny little dot, which is right here at x2, when it's displayed by your imaging system, looks like this, basically a blob, right? The size of that blob is the point spread function. If it's a really big blob, your point spread function is large and your resolution is low. If it's a really small blob, a little spiky thing, then your point spread function is thin, and your resolution is high, okay? And this is how you measure the point spread function on scanners. You put a little thing in there and you take a picture and you look at that, at the functional shape of that point spread function. Very practical. Usually, because the thing's so small, the height of this blob is pretty small, and you have to do this many times and average them to get a really good estimate of what the point spread function is, practically speaking. And so when you take those two little pieces of, now we break two pens and we get two balls and we bring them together, finally, the two point spread functions merge into one, and you can't see it, right? So that is called the point spread function. And looking ahead to those of you who are comfortable in working in either Fourier space or space, the point spread function, when you take its Fourier transform, you get the modulation transfer function, right? So the modulation transfer function, remember, it's units on the axis. When we go back and look at it, we're spatial frequency. So it was in cycles per millimeter, cycles per centimeter, something like that. The point spread function, its units are in space, right? So this half height here, which gives me the full width at half max, say, of this thing, is in millimeters. So it's in space, right? It's not in spatial frequency. And when you take the Fourier transform of that thing, you go into spatial frequency space. That's called the modulation transfer function. So that's how they're related. It's very similar. But you can measure them experimentally independently. Yeah.
If you look at image D, then you say like you can't separate between the two pictures anymore.
Right.
But if you have like some knowledge about the object or like tissue that you like image, then you could perhaps see that the amplitude of the signal is like unusually high. And
Yeah.
you can, like, so figure out how many distributions there are.
You can, however, once you get down to D, right, you know, I defy whether or not you can say that's just a larger, less dense object or two little dense objects. Those two things eventually become the same thing, like in integrating. Now, the one interesting thing about what you're talking about is like, can I somehow get in here because I have knowledge? I know what this function is. Can I improve my lot and perhaps increase the spatial resolution of my system? And the answer is, under certain circumstances, absolutely yes. You can increase the spatial resolution. And those circumstances are when you have isolated signals, right? So if I have a point spread function that looks like this, and I know that this is of an isolated signal because it's a tiny piece of coronary calcium, or it's a tiny piece of something in kidney, you know, what are the crystals you get in your kidneys? I forget what they're called, but it's really small. I get this blurry object, but I kind of know the object's right at its peak, right? And so this is called super resolution imaging, where you generate conditions such that the signal that comes out are from small objects, and you know precisely where they are. And this is done a lot in microscopy. And so in microscopy, if you have things that fluoresce, right, you get a blob, but the center of the blob is where that thing is. And so you can just go, forget about the point spread function or deconvolve it and say, that's where my fluorescence came from. As long as the fluorescence across the whole field is at a rate that they don't start overlapping, right? So if it's a slow blinking, a bunch of slow blinking lights, you can tell exactly where they're coming from, even though the point spread function is this wide. I just take its center of mass, and that's where the object came from. In more general terms, if you know this point spread function, you can do what's called deconvolution. You like just multiply in Fourier space by the inverse of the Fourier transform of this thing, right? So you amplify high frequencies in a functional way. Yeah.
So, I was wondering for like CT, do you have a lot of control over the resolution? Because I mean, like, it's kind of, you know, can the tech actually really make it variable?
No.
Okay, so
CT,
all from the detector.
CT, basically the resolution is set by the detector array mostly, and the separation of the detector elements on that array. And then in certain high resolution modes, the spot size of where the X-rays are coming from is important. So if it's a big spot size versus a small one,
They don't vary that, or is that all?
they do vary that, but for different reasons. Usually it's if a person is really big and you need a lot of X-rays to get a shadow, you usually make the spot size bigger to get more X-rays without burning out your tube, right? So, but that spot size actually, it will affect the resolution down around the point spread function. So yes. For point spread function, you would prefer the object to have no texture and just be a dot. And so in CT, that little ballpoint pen sphere, really we don't plan to actually image the texture of that object, because that is well beyond the spatial resolution, right, of our system. You can imagine that there is a way to measure the spatial resolution of a system by how the texture changes. If you had a complex texture that had a certain Fourier components, right, that had a kind of structure of frequencies in it, and you put it in your system and a different texture comes out, it's usually a smoothed one, then that smoothing kind of gives you an idea of what the spatial resolution is, right? Okay, so contrast in X-ray imaging is often defined as a fractional change in signal. And that is, you have a background signal, you have a target, which let's just say it's a tumor in the liver of a certain size or a lung nodule of a certain size. And there's your target. And in X-ray, as we'll see later when we look at X-ray physics, it makes sense to think of that contrast as a fractional change from the baseline, right? What we will measure in MR and CT though, and even in CT when we're looking at contrast to noise, we'll usually just measure the background noise if we can find a good estimate of it, and we'll measure the target signal and the background signal and use simple subtraction divided by the noise, and we'll do some examples. But I wanted to introduce this. This is in the book. And at times, this is very useful in X-ray imaging. So forgetting about the spatial resolution for the time being, let's just look at defining the contrast. So as you can see in the background here, I have what should be a uniform signal. It has some noise on it, so it isn't perfectly uniform. There are two things here that you would say are likely not from noise. Just like common sense, when you look at what's in that red box, you think, I think there's two things in there that are not just random deviations in the background signal, right? I think they're actually things, right? They're holes or something. And maybe there's a third one. I don't know about that one right there. So the question, what we'd like to decide is, well, what is the threshold for detecting something with confidence and saying, hey, that's an object in the background. That's not just noise, right? And so that's what we're going to talk about now. So we need a way to characterize the noise, and we need a way to characterize our object signal, right? And it's pretty simple. We'll work through an example in a minute. Time 11:48. So background noise. So here's an example of increasing noise with not changing the spatial resolution, not changing the underlying signal, whatever. You just add noise, right, to your raw data. And it looks like this. Finally, the noise hits an amplitude where it's swamping the signal, right? So the deterministic differences in signal from your actual object are overwhelmed by the complete random changes in pixel values from a noise process, right? And so where does it come from? In imaging and all these devices, all electronics have thermal noise associated with them. If you just have a resistor in space and you put clips on either side and you measure the voltage across that resistor, what you will see is something that just randomly changes, right? It's called, it's just thermal noise, right? And if you drop the temperature of that resistor, that noise goes down. If you heat the resistor up, that noise goes up. In magnetic resonance, we measure radio frequency energy that's coming from the patient. And if we don't elicit a signal from the patient, and they're just lying in a magnet, and so they have this polarization that's occurred in the protons. If I take a radio frequency coil tuned to the right frequency, and I hold it up to the patient, actually, even if it's not tuned to the right frequency, I hold it up to the patient, and I look back on my scope, I will see the noise go, it'll go up when I put it next to the patient. When I take it back out in space, that noise goes down. And so it's the thermal agitation of the charged particles in the patient that are causing the noise in this coil, right? And so that is something that's always going to be there. We need to make a signal that is higher than that background noise. That noise is very well behaved. It occurs at all frequencies, right? And if you look at that noise across time, you can shift your time window and it stays the same. It doesn't sort of go up and down and have, you know, changes like that. It's called ergodic and white. So it's got all of the frequencies. That's why it's called white. Its spectrum goes all the way out to the high frequencies. And it's truly a set of random numbers, right? If you digitize them and typed out those numbers as the voltage per unit time, those would be truly random numbers, right? Not correlated with each other at all. Okay? And then in X-ray, we have uncertainty also in the process by which the X-rays interact with the matter. And it gives you basic uncertainty in photon counting statistics, which isn't a big deal if you get the number of photons above about 20 or 30, but it starts to become a major source of uncertainty when the photons are around 10 and things like that. Just the photon statistics of counting affects you. Two other things we'll just mention: clutter and artifact. You'll see these terms. Clutter is complexity in the imaging field such that you can't see your target because it's just, you're overwhelmed with too many detailed signals. This is like the Where's Waldo effect, right? It's like Waldo's your target and you look and it's the circus is so complicated, it's hard to find Waldo amongst the stuff. Same thing happens in radiology. Although it's not Waldo, usually it's something else. An artifact is another source of signal that you truly don't want. But it's not random signal. It's something about your imaging system that has produced a signal that is not your object, but is highly correlated, right? So it could be like a mirror image of your object that's added onto your object, or it could be a big streak through the object. Those are called artifacts. They're not random noise. They're things you want to get rid of. But my statement about artifacts is one person's artifact is another person's technique, right? If you can make a signal, right, and you know how that signal behaves, it's one thing to get rid of it, you know, but it's another one to say, hey, this signal is from flowing blood. You know, why don't we invent a technique using that artifact signal that measures blood flow, right? As opposed to just getting rid of the signal. So that's a good policy to carry around with you if you're in imaging, is like people show you these artifacts all the time and say, well, how could we turn this into an image that is useful? So the signal to noise ratio here, it's very high because the random pixel values in the background and the random pixel values that are added on top of the image are of low amplitude. As we can on the last page, we saw as the noise increases, we go here. What we can do as the noise increases is we can blur the picture, and then our signal to noise, the ratio of the signal height to the random fluctuations in the signal, may stay constant, but our resolution goes down, right? So we're essentially sacrificing resolution to keep the signal to noise the same under those conditions, right? And so as we go a diagonal across here, right, we might have the same, maybe here, the same signal to noise, but it's a lot blurrier, okay? So there's a trade-off between spatial resolution and signal to noise, and that trade-off is performed in CT by the manufacturer under the hood, which is a little frustrating, but you have to know what's there. So here's two examples where we have, this is a phantom. It's a 3D printed vessel that is based on the shape of a heart, right? This is the endocardium. This is the blood pool. This is myocardium. There's contrast agent in water here. This is the material used in the printer. So we get these two different signals. This should be completely uniform, this signal, because it's all the same material, right? And so should this. And then when we look at what happens when we drop the MA Let me see, do I have it down here? Doesn't look like I wrote down what it was. But we use fewer photons, and so we get a higher amplitude of noise, okay, in the background. And you can appreciate that easily. And so the question is, how do you quantify it? You can take a region of interest that, you know, comprises a whole bunch of pixels, and then you calculate the mean here and the standard deviation around the mean. So we assume if you do a histogram, as we'll see, many of these things come out to be a normal distribution or a Gaussian, and you take the mean value as the true value of the background, and then the standard deviation measured in the background of these pixels. In this case, the standard deviation is 29 and the mean is 673, okay? Over here, the mean is 676, so it's basically the same. The amplitude or the height of the signal is exactly the same, but the standard deviation over here is only 10.8, okay? So this, you say, okay, signal to noise is better here than it is here. Visually, it's easy to appreciate. Quantitatively, you just do that ratio. Signal divided by the root mean square deviation of the noise. In this case, we have a very nice large field of view that we can actually do statistics about the variation of the pixels that should all have the same value, right? So you can do those statistics in this background because every pixel in here should have this mean value, right? In some images, it's really complex, and so it's hard to find a spot in the image where you can make that or believe that assumption, right? But if you have a little spot, here we'll draw a box here. This is going back to that image that we thought had two objects in it, and we'll draw a spot in the high signal to noise image, and then this is a lower signal to noise image. We'll take the same area. This is called a region of interest. You just draw a region of interest, and we're going to do statistics in there. We take the mean value of the background here, and it's 195. Mean value of the background here, 192. So that's essentially the same, right? When I plot the value of every pixel in this region of interest on a histogram, I get a function that looks like this. And the width of that function is the standard deviation around the mean. And the standard deviation is 3.4. And so it's 195 plus or minus 3.4 would give me 66% of all pixels, right? Plus or minus twice 3.4 would give me 95% of all pixels in there. Right? This one, same mean, but a much wider standard deviation when I look at the histogram. These two histograms are on the same scale, and now I have a much wider histogram. 8.3 is the standard deviation, right? And so calculating the signal to noise or the contrast to noise, let's say, of, say, this object versus the background, I will use the standard deviation I've measured in the background. I'll assume that the standard deviation in this little hole is the same for the pixels in that hole. That's, you know, the same. So we can draw a line through that signal and measure its amplitude as a function of position. So here we saw it was 195 was the mean. That's the background. Right in the center, and you can see there's a few pixels here, just one pixel here, right in the center. It goes down to 115. So now I have a contrast that I've measured, right? 115 minus the background signal 195, divide that by the root mean square deviation, standard deviation of the background, and I get this number, negative 23.5. And so that tells me that the contrast to noise between this target and the background is minus 23.5. That is a huge amount of contrast. That's way, way more than a person needs to say with 99.9% confidence that is a target, right? Over here, it's a little bit different. So now we look at our target, and it, because of the reduction in spatial resolution, probably got smeared a little bit, for one thing. And the standard deviation of the background, remember, was 8.3. So when I take 192 minus 156, which is the minimum that I achieve here, right, I only get a contrast of minus 4.3. And this is right on the threshold. This is called the Rose criterion, is that if that number, the contrast to noise, is 5 or greater, you have about a 95% chance of getting the call right every time, that the target is there or it's not, right? And so that gives you kind of the threshold that machines would operate comfortably at. Humans, however, are not comfortable operating around here. So if I'm a radiologist and I look at this thing and I say, is this an object? Actually, practically speaking, I'm probably not going to call it positive, because, you know, you look over here, that looks the same, that looks about the same, right? And they're in the background. So the distinction of that thing from the background, how far out of the histogram is it sitting, right, is what, you know, you're doing in your head. So if I have an object that's sitting right here and it's still kind of inside the histogram of the background noise, it's very uncomfortable. If the contrast to noise is 20, right, so that's 20 3.4s, right? So you're way down here, right? And you're not even close to that histogram. And so you're very, very confident that that thing's a target. It's not something that just by chance occurred, right? So humans work a little bit higher, probably comfortably, than the Rose criterion, which is 5, which is simply hard statistics. If you made a machine make the decision, you know that you're going to be right 95% of the time. But humans don't want to operate there. They'd prefer clearer pictures, higher contrast pictures than that. Okay. Any questions on that? We're gonna go to X-ray physics now, which is a bit of a different topic. Okay, great. This is an X-ray image of a hand, right? And the brightness in this picture is proportional to the number of X-rays that got stopped when they were trying to get through this hand, okay? So the background, no X-rays got stopped at all. They just went straight to the detector, okay? And it comes up black. Really, it should be reversed, right? It should be, this should be bright, because that's what happens in a film screen system, but digitally it doesn't matter. And here in the bone, many X-rays got stopped, so it's bright. And this is the way CT images are displayed, et cetera, is like brightness means a lot of X-ray absorption. And a bonus for anyone who knows how to tell whether or not that's the right or the left hand. Okay, you can just take that home and ruminate on that. So this is the basic, you know, planar X-ray system that we saw when we first started. We have an X-ray source here. There's going to be some filtration and beam manipulation of the X-ray beam coming out of here. And those X-rays go through the patient, and then there's a detector behind the patient. And this setup is often used for interventions and, you know, that swallowing technique, et cetera. So the electromagnetic spectrum shown here with the photon energies of the relative frequency. So here's the wavelength up here, right, of the EM radiation. Here's the energy of a single photon at that wavelength. And radio waves are all the way over here, right? This is where we're going to do MR. And X-rays are all the way down here. So the wavelength is like 10 to the minus 10 meters, right? The energy of a photon with this wavelength is somewhere between 70 and 140 keV. And we'll show how what that relates to in terms of X-ray production in a moment. We'll show it right now. So this is an X-ray tube. These devices are the heart and soul of every X-ray imaging device. You have one of these X-ray tubes. It's like an X-ray light bulb. And, you know, it has a motor side and a cathode and an anode. And I think, do I have it? Yeah. I'm going to flip it upside down because our diagram is in this orientation. So this is a motor here. And there's an axle along here that's like a spindle. And then this is the target that we're going to hit with electrons to produce X-rays. And that target spins very fast, like 4,000 RPM or something around this way. And that's what the motor's for, is to spin this target. Down here, sorry about the reflection, but down here is a cathode, which literally just heats up like a normal incandescent bulb, but it has a special material that boils off electrons, right, when it heats up. And what we do is we put a very high positive voltage on here, negative voltage on here, such that the electrons, when they come off of here, there's a field, an electrical field right here, and they shoot across that gap because there's that electrical field. They're a charged particle. They see an electrical field, they just go zoop and start accelerating in that electrical field. And I think one of the problems in the problem set, we'll figure out what is the top velocity of electrons when they hit the target, right? And I'll give you a hint, it's not a small velocity, it's a large velocity. So that diagram, which is a bit easier to understand, you have this anode, which is often it's this, it's either tungsten or molybdenum, and it is spinning in this vacuum. It is cranked to a high voltage, 70 to 140 kilovolts are here between, you know, this would be ground here. The cathode assemblies here, it's a tungsten filament running really hot. And one of the things we can adjust on our X-ray system or a CT scanner is this tube current. So how much current do we put through this cathode? So we can crank it up and make more electrons come out, or crank it down and make fewer electrons come out. And here, between 70 and 140, that will affect the spectrum of X-rays that are produced, because it affects how much acceleration occurs for the electron as it goes across the gap. Low voltage, they're going to hit this slower. You're going to get lower X-rays, lower energy X-rays. High voltage, this accelerates faster. You will get higher energy X-rays coming out. There's a little, usually a rectangle on this target, and the target is spinning. And so the continuous sort of impact of electrons on that substance heats the substance up a lot. But you know, because it's spinning, it averages that heat around, and the heat is usually drawn off via conduction. Okay, these are a big deal in this field, and in CT, you need electron or X-ray sources that produce very high fluence of X-rays, because we want to image very quickly. So if we make a CT scanner where we're only radiating the patient for, say, 100 milliseconds, we need a lot of X-rays in that 100 milliseconds. So that means these tubes have become more powerful, more powerful, more powerful over time. And they've become way more expensive over time. So if you blow one of these tubes, you know, it's maybe 100 grand for that light bulb, right? So, or more. And that's why you have these service contracts on these machines, because eventually you blow one. So we're going to quickly look at how the electron, when it hits this target, what physics is going on to produce X-rays out of here from that collision. So I get an electron goes in there, hits the target, and then some X-rays come out, right? So the thing that's causing most of the heat is just essentially collisions of the electron with electrons in orbitals right, around that atom. And so what happens is you knock this electron this way, and this one collides with the electron and goes to this next atom, and the thing just happens over and over again. And this results in heat, right? It doesn't produce any photons or radiation. It's just electrons banging into each other, and you have a shower of electrons going through the material. And that just causes heat. What we're interested in is the stuff that causes X-rays to come out. And so an electron can come in here, and it can actually interact with an atom and knock one of the electrons of that atom straight out, right? And a electron in one of the outer orbitals can fill that spot. It'll drop down and fill that lower orbital that's close to the nucleus. And in doing so, when it does that transfer, it loses energy as a photon, okay? And that photon comes out usually as a characteristic X-ray, it's called, which is in the 100 kilovolt range, okay? That's called characteristic radiation, but the primary source of X-rays is from bremsstrahlung, bremsstrahlung is the German word for braking. And braking, not snapping, but braking, like hit the brakes, right? And so the electron comes along, it gets close enough to the nucleus to interact, and the trajectory of the electron is diverted. It bends. And so there's a momentum change in the electron. It'll slow down and change its direction. And in doing so, in that interaction, a photon is created, right? And so these bremsstrahlung or photons are the primary source of X-rays coming out of our X-ray tubes, right? When you look at the energy of all of the electrons that are coming out of that tube, they're not all just at one energy, they're at a whole spectrum of energies. So if we put the voltage across the anode to cathode at, say, 100 kilovolts, right? Then the highest energy X-ray we can achieve is 100 kV X-ray. That's if this collision occurred and it was a perfect hit, right? A perfect reflection, and all of the energy of this electron was transferred to photons, right? Then you'd get 100 keV photon come out of here if this one had enough kinetic energy that it was 100 kV electron, right? So that doesn't happen with great frequency, right? That perfect collision. Collisions occur at different angles, which produce lower and lower energy X-rays as that angle gets lower and lower. So if I have just like this, it just grazes it and changes, this will be a low energy photon or low energy X-ray coming out, okay? And so as those angles change, we get more and more and more photons with these lower energies coming out. It left to its own devices, if this wasn't an X-ray tube, this function would just keep going towards zero up here. That would be the relative numbers of photons at different energies. However, what they're produced, right, by these collisions, but the lower energy X-rays, they just immediately get absorbed by the target material itself, right? Or they get absorbed by the glass, outside the tube or something like that. They're really low energy. The stopping power for low energy of most materials is quite high. And so they just don't make it out, right? The other thing we can do is we often put a piece of copper or aluminum right in the way of the beam of X-rays, and it's a very thin piece, and it filters out many more of these low energy X-rays. Because when we're shooting X-rays towards a person, there is no point in shooting a whole bunch of low energy X-rays to the person, right? Because those have zero probability of getting through the person. So all they will do is deposit energy in the person, right? They don't make any kind of contrast. They don't they cast a shadow that is perfect. It's just like, it's like photons. Like when you look at yourself, not many photons get through your body, right? When you're casting a shadow. So light photons. So this is called the X-ray spectrum, and it will be different from machine to machine, or actually from X-ray tube to X-ray tube. Each X-ray tube that is the same product, same design, should have the same spectrum, close, right? But from one manufacturer to another, they all make their own X-ray tubes, and they will have slightly different spectra coming out of those. Some will have, higher energy stuff, some will have lower. And it's often dependent on what filtering they put in. Okay, so we got 5 minutes. So I'm going to do this one last thing, which is, now we've had our X-ray tube, we accelerate the electrons, they interact with matter, they produce X-rays, right? And so now I have an X-ray beam coming out. How do those X-rays get stopped by the patient, right? And I'll give you a couple of quick answers. One is, as the energy goes higher and higher, photons or X-rays or gamma rays will just go through more easily, right? They'll go through people more easily. And so if you have really high energy photons, many of them don't get stopped by you. They just fly right through you. Okay? As you go to low energy X-rays, down below, say 80 kV, down to 70, 50, whatever, you have a very good ability to stop them so none of them get through. And so what we're going to do is we're going to work somewhere in the middle there, where the X-rays are just the right energy, such that, say, about half of them get through, right? That would be a good number. So we'll take a look at the three components of this interaction. The two principal ones are the photoelectric effect, Compton scattering. Photoelectric effect, essentially what happens is the incident photon comes in, interacts with an electron. This is sort of what was happening before with the electrons, right? But in this case, a photon is coming in, right? It hits an electron and ejects that electron as a photoelectron, okay? And then a higher energy electron in a higher orbital will drop into that location, into that orbit, and give off characteristic radiation, okay? So we get two things there. We get attenuation of this original photon, but we get this characteristic radiation come out, right? We don't really want this thing because we're probably going to detect it. But if it's at a different energy, you can eliminate it. But it is a way of stopping photons. Remember, all we want to do here is stop the photons, because with a sort of relative probability to make a shadow. Another two-step effect is, this is called the Auger electron, where the photon comes in, knocks out a photoelectron, and when the system drops or changes energy, instead of emitting characteristic radiation, it actually emits an electron with the same energy, right? With the required energy for this transition to this ionization transition to occur. And it just comes out as an electron as opposed to a photon. That's called an Auger electron. So this whole thing is photoelectric effect. Another, and this is most, I think, of the interactions with matter that we're going to see at the energies we're working at, is this process called Compton scattering, okay? So a photon comes in, hits an electron, the photon itself is scattered off at an angle, right? And then the Compton electron gets shot off into the object. And ideally what happens is this angle is high enough such that when this Compton scattered photon gets to your detector, it's at a high enough angle that you can filter it out with what's called a scatter grid, with parallel planes, parallel lines that look back to the target. And if this thing comes at an angle, it stops it. And so then we've eliminated this photon, right? The effect of that photon is gone. And so this is the two primary ways that the photons interact with matter, and we'll start here on Monday. Okay. Alright.
I sent you the email, the problem is here.
Oh, no, I got it.
Okay, okay.
Yeah, I just haven't had time to answer yet, so, yeah. But I did get it, I'm pretty sure.